Hey guys, Mr. Mar with another video over power series. In this video, we're going to work one example from the textbook and then do example 2 and 3 from the notes on power series. So we'll get started with this example. So we're finding the radius of convergence and the interval of convergence for this power series. So the first thing we do is check the limits as n approaches infinity of an plus 1 over an. And this limit is going to be less than 1. So if we start out, we will get, let's do a bunch of side work before we actually substitute the limit in. We'll have x minus 3. If we substitute in n plus 1, we would get n plus 2 over n plus 2 times 4 to the n plus 2 power. So this is the an plus 1. And then dividing by an, we would have really the reciprocal of this sequence. So that would be n plus 1 times 4 to the n plus 1 over x minus 3 to the n plus 1 power. And so we don't need the absolute value. We don't have anything negative really. So the next thing that we do is we go through and cancel out some stuff. So x minus 3 to the n plus 2 divided by x minus 3 to the n plus 1. All of these cancel and we're left with 1 here. For the 4 to the n plus 2, all of these cancel and we're left with just 4 to the first power here. And once we apply our limit, we're going to get the limit as n approaches infinity of just x minus 3, and then we'll say like x minus 3 over 4, because neither one of these have an n, and then multiply it by n plus 1 over n plus 2. So then in absolute value, this is less than 1. Since the x minus 3 divided by 4 isn't affected by the limit, we move that out to the front. We get x minus 3 over 4 times the limit as n goes to infinity of n plus 1 over n plus 2. And we can still put the absolute value on this, same thing. So out to infinity, this is going to converge to 1 because we have n over n. So the degree of the numerator is the same as the degree of the denominator. So it's the limit is the ratio of the leading coefficients. So 1n divided by 1n is just going to be 1. So we end up with the absolute value of x minus 3 over 4 is less than 1. So once we remove the 4 from our denominator by multiplying by 4, we get x minus 3 is less than 4. So our radius of convergence is r equals 4. Oh, I'm sorry, you can't see that. So our radius of convergence is r equals 4. We zoom out just a little bit. So to find the interval of convergence, we solve this inequality. Anytime we have an absolute value inequality where it's less than, we put what's inside the absolute value between positive and negative 4 in this case. So to solve this, we add 3 to the outsides, and we would get negative 1 is less than x, which is less than 7. So the question is, do we include the 7 and the negative 1? So we have a working version of our interval of convergence. To determine if either one of these is less than or equal to, we go back to our original sequence and substitute in -1 and +7. And so whatever we get when we substitute into the sequence will tell us if the series actually converges. So we're first going to try x equals -1. So if x equals -1, then if this is -1, we'd have the sum from n equals 0 to infinity of -4 to the n plus 1 over n plus 1 times 4 to the n plus 1. So a shortcut is -4 to the n plus 1 is equal to -1 times 4 to the n plus 1, which equals -1 to the n plus 1 times 4 to the n plus 1. So as a rewrite, this series is now the sum from n equals 0 to infinity of this, the 4 to the n plus 1 divided by 4 to the n plus 1 cancels out. So what we have is -1 to the n plus 1 over just n plus 1. So this series is an alternating series because the terms alternate in sign. Our test for the alternating series is, do the terms decrease in magnitude, do they have a limit of 0, and do they alternate signs? So clearly they alternate signs because it's an alternating series. We'll put a bullet here. They decrease in magnitude and the limit as n approaches infinity of -1 to the n plus 1 over n plus 1 equals 0. Well, in absolute value, the limit equals 0. So if we were just looking at a like as a P series, or if we did the integral test, this sequence would diverge in absolute value. So it's not absolutely convergent, it's conditionally convergent. But this still converges when x is -1 because it's an alternating series. It decreases in magnitude and the limit as n approaches infinity is 0. So we can include the -1 as a part of our answer. The second thing we check is if x equals 7, then we would just end up with, like, again, referencing this sequence. If x was 7, we would have the sum from n equals 0 to infinity of 4 to the n plus 1 over n plus 1 times 4 to the n plus 1, which this is the sum from n equals 1 to infinity of just 1 over n plus 1. And this sequence is divergent because the comparison sequence 1 over n is also divergent. So we don't include the 7. Divergent, and the reason is p equals 1. So in this case, our interval of convergence is -1 to 7. We could write that as -1 to 7, like so. So our radius of convergence is r equals 4, and our interval of convergence is -1 to 7. So we're going to jump to example 2 in the notes, and we'll see what happens when we get to special cases of R. So we're working this problem, the -1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. So the first thing that we check is the limit when n goes to infinity of, so we're going to have -1 to the n plus 1 times x to the, so if we substitute in n plus 1 for n, that's going to be 2n plus 2 plus 1. So 2n plus 3 divided by 2n plus 3 factorial. And when we divide by an, we're going to be dividing by 2n plus 1 factorial over -1 to the n times x to the 2n plus 1 power. Doing a little bit of side work. Let's see, 2n plus 3 factorial equals 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So if 2n plus 3 factorial is this, then it cancels out 2n plus 1 factorial, and what's left over is 2n plus 3 and 2n plus 2. So we're going to keep that in mind. And then the -1 to the n and -1 to the n plus 1, well, we're just left with -1 to the first power. This completely cancels, that goes away. And then x to the 2n plus 3 divided by x to the 2n plus 1, all of that cancels, and we're left with just x squared instead. So the rewrite on our limit is, we'll put it down here, the limit as n tends to infinity. So we end up with just x squared, which we don't need inside the limit. We'll put the absolute value of x squared on the outside. So the absolute value of x squared times the limit as n tends to infinity. And remember, we said that the 2n plus 1 factorial divided by 2n plus 3 factorial simplified to be 2n plus 3 times 2n plus 2 in our denominator. So we'll have an absolute value. The -1 won't matter in absolute value, so we can just have 1 over 2n plus 3 times 2n plus 2. And when this limit tends to infinity, this is going to be going to 0, because we have no power of n in the top and the highest power is in the bottom. So the answer for when this is less than 1 is always, because if n is a positive number, 1 divided by some number that's always going to be larger than 1 is always going to be true. So this is going to be x squared times 0 in absolute value, which is always less than 1. So r equals infinity in this case, because for every value of n, this converges. So for every value of x, this is also going to converge. So we're just going to put convergent everywhere. And so our interval of convergence is -infinity to infinity. So for all values of x, this series converges, because we get a radius of convergence of infinity. Because for any value of n, this is going to be less than 1. For example 3, we're going to run into the opposite case, but we'll see how that develops. So the same check, we start out with the ratio test, the limit as n approaches infinity of n plus 1 factorial times x minus 3 to the n plus 1 power divided by n factorial times x minus 3 to the n power. So a similar trick is if we have n plus 1 factorial, that equals n plus 1 times n factorial. So if n plus 1 factorial is n plus 1 times n factorial, in the numerator, well, in the denominator, the n factorial cancels out, and this turns into just n plus 1 without the factorial, because we took out an n factorial from n plus 1 factorial. And then the x minus 3 to the n plus 1 divided by x to the n completely cancels, and we're left with an exponent of 1. And so this is equal to, we just end up with x minus 3. We'll put that on the outside. We have x minus 3 in absolute value times the limit as n approaches infinity of, what's it, just n plus 1? So n plus 1 in absolute value. And the question is, for what value of n is this limit less than 1? Well, n starts out at 1, based on our sequence. So, or based on the starting value of the series. So if n is 1, we're going to start out with 2. 2 isn't less than 1, and then we just keep getting larger. So this limit is infinity because n grows unchecked. So in this case, the limit as n tends to infinity for the absolute value of n plus 1 equals infinity, which is never less than 1. It's always greater than 1. So this only converges when x equals 3. And then it's only trivially convergent at that point. So if x equals 3, then you just have the sum of 0. So technically that's convergent, but it doesn't really mean anything. It only converges when x equals 3. And that reason is there's no other value for x that this can converge, because if we do, we have some either non-negative or we have some non-negative or negative value that multiplies by n factorial to create a very large alternating series or an always positive factorial series that doesn't converge. So again, this only converges when x equals 3 because the limit is infinity. So in the 3 examples we worked in this video, we saw another example of where we actually had a radius of convergence. In the first example, it was 4, and we checked our endpoints to see if we should include them in our answer. In the case of the first example, we did include -1, and we didn't include 7 because when we substituted in -1, we got an alternating series that did converge because it passed the alternating series test. And then for x equals 7, it failed by comparison to the p series. For the second example, we had a radius of convergence of infinity because this limit is always less than 1. And then for the third example, we had only convergent when x equaled 3 because the limit was infinity, which is always greater than 1 and not less than 1 as the ratio test dictates. So in our next video, we'll cover writing power series as geometric series. See you there.